You flip a switch and boom, the light comes on. It feels instant, right? Like you've unleashed a tiny bolt of lightning. But what if I told you this stuff making that light, the electricity itself, is actually crawling along slower than a snail? Well, today we're going to tame that lightning. We're breaking down the fundamental rules of how electricity really works, how we control it, and yeah, what happens when we lose that control.
So here's our game plan. First, we are going to absolutely demolish that myth about the speed of electricity. Then, we'll get into the push and pull forces that are constantly at war inside a wire. We'll uncover the one beautiful law that governs it all, see how that lets us build different kinds of circuits, and finally, we'll step into the danger zone. What happens when those circuits go wrong?
All right, let's dive right in with that shocking truth I mentioned. We all have this gut feeling about how fast electricity is, but I'm willing to bet that feeling is completely and totally wrong.
I want you to really think about this for a second. You hit that switch, the light is on. Feels like it's got to be moving at the speed of light, right? But how fast are the actual little particles, the electrons, carrying that charge? How fast are they really moving down that wire?
Yeah, we all picture lightning trapped in a copper tube. But the reality, well, it couldn't be more different. The actual speed is, and I am not exaggerating here, just astonishingly slow.
Get ready for this. The actual calculated speed of an electron drifting through a wire is 0.58 centimeters per minute. Yeah, you heard me right. That is quite literally slower than a garden snail. So, what is going on? How does your light turn on instantly?
So here's the solution to that puzzle, and it's actually pretty cool. I want you to imagine a tube that's already jam-packed full of marbles. The individual marbles, those are our electrons. They barely move at all. But the second you push a new marble in one end, another one pops out the other end almost instantly. See? That push is the electric field, and that's the thing that travels at nearly the speed of light, not the electrons themselves. So that push and the friction that those electrons feel, those are the two key forces we really need to wrap our heads around. You can think of them as the yin and yang of every single electrical circuit out there.
Let's start with the push. A battery isn't some magic box that creates electrons out of thin air. They're already in the wire. The battery just acts like a pump. A water pump creates pressure to get water moving, right? While a battery creates an electric pressure difference. We call that voltage, and that's the force that gets that whole chain of electrons moving.
Okay, so if you've got a push, you've got to have something pushing back, and that's resistance. It's basically electric friction. As those electrons try to flow, they're constantly bumping into atoms in the wire, and that opposition slows them down. All that bumping and friction converts electrical energy into heat, and that is exactly why your phone charger gets warm when you use it.
So we have the push, voltage, and we have the friction, resistance. Then this brilliant German physicist, George Ohm, comes along and figures out this incredibly simple, elegant relationship that connects them. He gave us the key to making electricity predictable and controllable. And here it is, Ohm's law. It's beautiful. It just says that the voltage is equal to the current, which is just how fast the electrons are flowing, times the resistance. V equals I times R. This one little formula, it's the foundation for pretty much all modern electronics.
Okay, so a formula is great, but how do we actually use it? Well, let's see how Ohm's law plays out in the two most basic ways you can wire things up, in series and in parallel.
Let's break down the difference. Think of a series circuit like a single-lane country road. All the traffic, that's our current, has to follow the exact same path, one car after the other. Now, a parallel circuit is more like a big highway with multiple lanes. The traffic, our current, can split up and take different paths to get to the same destination.
So, on that single-lane road, since all the current is the same everywhere, Ohm's law tells us the voltage gets shared, or divided, among all the things in the circuit. Something with a high resistance is like a steep hill. It takes a lot more energy, or voltage, to get through. This is a super useful trick for things like dimmer switches.
Now, on our multi-lane highway, it's the current that gets divided. The total flow of traffic from the start splits up among the different lanes. And just like we all do, electricity takes the easy way out. The path of least resistance, the lane with the least traffic, is always going to get the most current.
All right, so we know the rules for keeping electricity under control. But what happens when we break those rules? Now we're heading into the danger zone to look at two very common and potentially very bad ways that circuits can fail.
First up, the infamous short circuit.
This is what happens when electricity finds a shortcut it was never supposed to take, a path with almost zero resistance to slow it down.
And just look at what happens. Ohm's law tells the whole story. If resistance drops to basically nothing, what does the current have to do? It skyrockets to an insane level. All that current generates a massive amount of heat almost instantly, and that's what melts wires and starts fires.
Now, the opposite problem is an open circuit. This is just a simple break in the path, like a cut wire or a light bulb that's burned out.
So in this case, the resistance of that air gap becomes basically infinite and it stops the current cold. Nothing flows. But here's the trap. The entire voltage of the power source is now sitting right across that tiny gap. And even though nothing is working, that gap is live, just waiting for something like you to come along and complete the circuit.
Okay, so let's bring it all home. We learned that the speed of electricity is just an illusion created by a super fast electric field, not the slow-moving electrons. We saw that voltage is the push and resistance is the pushback, and the relationship is perfectly captured by Ohm's law. That law lets us build series circuits to split up voltage and parallel circuits to split up current. And we found out that breaking the rules leads to dangerous shorts with way too much current or sneaky opens with no current at all.
And all this brings us to one final really interesting question. We've seen resistance as this thing that wastes energy as heat, but it's also the only tool we have to precisely control voltage and current. So what is it? Is resistance an essential, helpful tool for engineers, or is it a fundamental flaw of physics that we're always just trying to work around? Something to think about. Thanks for joining us for this explainer.